Hey, welcome to the video. This video I want to discuss the ambiguous case for the law of sines. On the screen, I already have a picture of an oblique triangle with the law of sines written to the right hand side. The law of sines states that a side length of any triangle, side lengths are labeled lowercase letters. So any side length and divided by sine of the angle opposite. When we say opposite, we mean if this is side A, angle A is opposite, or vice versa. If this is angle B, side B is opposite angle B. You can take a side length, divide that side length by sine of the angle across from it, or opposite, and that is proportional to either of the other two ratios. That's your law of sines. So the ratio of side A over sine of angle A is equal to the ratio of side B over sine of angle B, which is also equal to the ratio of side C over sine of angle C. In this video, I want to discuss a special case of the law of sines, which is known as the ambiguous case. The ambiguous case now what we mean by the ambiguous case is if we have a triangle such that we know two side lengths, and a non-included angle, then we don't know immediately if the measurements that we're given are measurements for one single triangle, two triangles, or possibly no triangles, right? So I want to start with this picture right here, which is just basically an angle. And I'm not going to close this as a triangle yet. I'm not going to draw that third side. What I want to discuss before I actually label side lengths and an angle measurement for this particular potential triangle, before we label this triangle with side length measurements and an angle measurement, let's first discuss the height of a triangle. The height of a triangle is always perpendicular to a side of that triangle, known as the base, right? So the height of a triangle and the base of a triangle are always perpendicular. So if I picture this potential triangle and I say, okay, well, I want to find the height of this triangle. Well, the height of this triangle can be found. All right, let's assume the height is the segment from vertex C perpendicular to side AB. We'll label that H. Okay, now look at the picture. We have a right triangle within our picture. In any right triangle, you can use Sohcahtoa. Sohcahtoa is an acronym that is used to help us remember that sine of any angle is equal to the ratio between the opposite side and the hypotenuse in a right triangle. Cosine of any angle is equal to the ratio between the adjacent side and the hypotenuse side in a right triangle. Tangent of an angle in a right triangle is equal to the ratio of the opposite side over the adjacent side. So I can use Sohcahtoa to come up with a general height for this particular triangle. if I say, let's look at angle A. Well, I know sine of angle A is equal to the opposite side, which in this case, opposite of A would be what I've labeled H, over the hypotenuse. So the hypotenuse would be across from the right angle. So in our case, based off the vertices that I have labeled, if my right angle is here, so let's assume B is there, so we can label the hypotenuse B. All right, now what can we do to get H by itself? Well, we can multiply by side length B. So B times sine A is equal to H. Okay, so that is very, very, very important. Okay, so keep that picture in mind. Now let's look at that general picture once again. Angle A, angle C would be up here, and angle B would be somewhere over here. Took a little while for that to show up again. So we have angle A, angle C, and angle B. We don't know where angle B is. Now, the most important part to figuring out how many triangles we potentially have in the ambiguous case is finding that height. If we can find the height of that potential triangle, we can use that height to compare with the two sides that we are given measurements to determine if we have a triangle, and if we do we have one or do we have two triangles? So the height is very, very, very important. Okay, so now let's think about this. If we have a potential triangle where we are given side length A, angle A, and side length B. So in other words, let's say angle A is 43 degrees. In a dashed line, let's label what side A, where side A could be, right? If we close that triangle with a dashed line, side A would be over here. That side length is 81. And let's say side B is 62. If I know two side lengths and a non-included angle, that means if I know side A and side B, if those measurements are known, the non-included angle in this case would be angle A. When we say non-included, we mean one of the two angles that is not between the two sides that we know. So very briefly, in this case, if I know side A and side B, then the included angle would be angle C. The ambiguous case appears if we have two sides and a non-included angle, one of the two angles that is not between the two sides, okay? Which is what we have right here. Now the trick in determining we have 0, 1, or 2 triangles is finding that height. Okay, so if I draw a segment from vertex C perpendicular to side C, and I label that H, well, let's find out what H is. Okay, so using Sohcahtoa, we would say sine of angle A, which is 43, so sine of 43 degrees is equal to, now we're finding H, so we would say H, which is the opposite side, over the hypotenuse, which would be side B, so we'd say over 62. And now, if we type that into our calculator, being sure that we are in degree mode, so then we get about, let's round 1 decimal place, about 42.3. So H is approximately 42.3. Okay. In this example, do we have a triangle? Do we not have a triangle? Or do we possibly have 2 triangles? Well, to determine that, we want to compare side length A to the height and also to side length B. Okay. So if I look at my picture, my height of my triangle here would be about 42.3, whatever unit of measure you want to discuss. Inches, centimeters, so on. So what we're going to do is compare side length A to the height and at the same time compare it to side length B. So if side A is larger than the height, then we know we at least have 1 triangle. Okay, so let's kind of picture this real quick. It should be coming up. So since the height is approximately 42.3, if side A were less than that, I know in our case we have side A is 81, but let's assume A was less than H, right? H is 42.3. Let's say that we had a side length A that they told us was 40. Well, that cannot be possible, right? Because if the height is 42.3 and side length A is less than that, there would be no possible way to close this triangle with that third side. It wouldn't be possible because we could not close that third side. We could not close the triangle, right? So let's say A was 38, but our height was 42. Well, 38 is less than 42. So you can kind of picture that there would be no possible way of closing that triangle. Okay? So if A is less than the height, or if the side opposite of the angle that you're given is less than the height, then there's absolutely no way there could be a triangle. Okay? Now, in our case, side A is larger than H, which is good. That means we are able to close this triangle. Now the question is, do we have 1 triangle or do we have 2 triangles? Well, comparing A with H helps determine if we have at least 1 triangle. So since we do have an A value that is larger than the height, our A is 81, our height we found was about 42.3. That tells us we definitely have at least 1 triangle. Now the question is, do we have 1 or possibly 2 triangles? So if we draw another general picture, let's say our A was greater than 42.3, so we have a triangle, but let's say it is, what if A is greater than 42.3 but less than 62? So A is in between the values of the height of this triangle and the other side that we know. If this is the case, then we have to have 2 triangles. There must be 2 triangles. And the reason there's 2 triangles is because think about a barn door. A barn door can swing inside a barn or outside a barn. So if we have an A value that is greater than the height but less than the other side, for instance, let's say A was 50. Well, 50 is greater than 42.3, so that tells us we have at least one triangle. 50 is less than 62, so we actually have two triangles. So if A is 50, and the reasoning is because that side length that measures 50 could come inside. It could be here. Or it could possibly be on the outside there, like a barn door. Okay, so that's how to determine if you have two triangles. If A is greater than the height, but less than, in this case, side B, there are two triangles, and that's because A can swing in or out. Okay, so now what we had, let's draw again what we had. Now remember, what we want to do is compare side A, so the side across from the angle that we know. In this case, we know angle A. So we're going to compare side A with the height. Side A measures 81. So that's definitely bigger than 42. So we know we have at least one triangle. Now we compare 81 to 62. 81 is larger than 62. So there can only be one triangle here. There's no possibility for two triangles. And if we use the same idea above, where there were two triangles, we can prove that there can't be two triangles here. If side A has to measure 81, then there's no way possible for side A to be inside this triangle. There's no way possible for that barn door to swing inside. It must swing outside, right? Matter of fact, it would swing way out here. So that was just trying to determine how many triangles we had: 0, 1, or 2. Now at the end of this video, I will post a picture from a textbook that has these ideas in one nice table. Okay. But let's say we want to find angle B. That's all we can find right now, right? Because we have the ratio of side A and angle A, we can write 81 over sine 43 is proportional to 62 over sine B, using the law of sines. Now we would cross multiply and divide. So we would have 81 times sine angle B is equal to 62 times sine 43. And then we would divide by 81. Once we have sine B isolated, we can use the inverse sine function to find an approximation for angle B. So angle B is equal to the inverse sine, or arc sine, of that ratio 62 sine 43 over 81. So angle B is about 31.5 degrees. So if we know two angles of a triangle, we can add those two angles, subtract from 180 degrees, and find a third angle. So we know angle C is approximately 105.5 degrees. Now the only thing left would be to find side C. And you can use law of sines to find side C in this case. And side C would be approximately 114.2. This is the ambiguous case such that we only have one triangle. Now imagine how much work you would have to do to find the angle measurements for the ambiguous case when you have two triangles. Draw the pictures of the two potential triangles, sketch them. They don't have to be perfectly drawn to scale, but sketch them in a way such that you can see that angle B would be in one triangle obtuse, in another triangle acute. So in the ambiguous case where you have two triangles, you will see that the angle B would be acute in one triangle and obtuse in the other. I do plan on creating more videos. This is my first video. I hope it helped. Look for future videos. I will continue to improve. There's a lag between my iPad and my computer, so I will look to adjust that so there's not as long a delay in things that I say and things that you see on the screen. Thank you for watching. Again, look for future videos, and I'll see you soon.